Well, class, so has anyone checked out the extra credit solutions that I posted? Any of you guys that turned in those hard problems? I'm curious if anyone's looked at the solutions that I posted. I wasn't sure if you guys know that I posted them because I didn't send an email, so it's like, how are you going to know unless you check the announcements on Triton Ed or check the course website? So I'm telling you now, if you didn't already know, you can go look at those solutions if you decided to do some of those problems and want to see if you did them right. Or if you want to see how I did them. Okay. Any questions on any stuff or things? Okay, so last time I was talking about section 10.7 on power series. We were doing a few examples, so let's do another example with power series about the usual question with power series is finding where they converge. So let's do another question where we find where a power series converges. Okay, how about, I'm going to try and create like a real funky one. How about, let's make it oscillate. Let's make it centered somewhere other than 0. Let's put a 3 to the n in there, and how about an n? So where does this power series converge? Okay, how do we figure out where a power series converges? How about, what was your name again? Zahar or so? Sorry? Zara, yeah, how about you, Zara? What tools do we have at our disposal to answer this sort of question? The what? Okay, yeah, so we want to find, okay, yeah, so this is a very related question to finding the radius of convergence. To find the radius of convergence, we have various tests, such as the ratio test and the root test. Most of these questions, you're probably going to want to use the ratio test. Last time we did an example using the root test. A lot of times, multiple tests will work. I think the ratio test is probably the easiest to apply, though. So let's try the ratio test on this guy. Which means, so this whole thing right here is like my AN, and I need to compute the limit of the n plus first term over the anth term. Okay, so an plus 1 over an will be -1 to the n plus 1, x minus 7 to the n plus 1, 3 to the n plus 1, n plus 1, over -1 to the n, x minus 7 to the n, 3 to the n times n. And let's see, I want absolute value of all this. So in fact, the negative signs just go away. And I'm left with, okay, well, I get to cancel a bunch of stuff. I get to cancel this with this, this with this. Negatives are gone. Okay, so I get a x minus 7 over a 3 and n over n plus 1. So now I can take the limit as n goes to infinity, which means this term goes to 1, and I just get x minus 7 over 3. So we want this quantity to be less than 1. So x minus 7 is less than 3. Good. So this series was centered, apparently it was centered at what number? At 7. So the distance away from 7 that our x's can get is 3. So this is our radius of convergence. Okay, great. So we're not done, though, because after you find the radius of convergence, so we know that it converges inside that radius. It diverges outside, but then there's the annoying 2 endpoints that we need to check. So part 2 of this, of any of these problems, is check the endpoints. Here, let me just see. Which are apparently 7 plus 3, which is 10, or 7 minus 3, which is 4. Okay, so at x equals 10, if we just plug 10 into the series, the series is negative 1 to the n, 3 to the n over 3 to the n times n. Right, the 10 minus 7 became a 3. Oh, well, this is a familiar series. We have a name for this one. It comes up so often. It's the alternating harmonic, which converges or does not converge. Who says the alternating harmonic converges? Only one person? No, it converges, yeah. I was hoping to see a whole sea of hands. I want to see like the wave or something. Yeah, this guy converges by the alternating series test. So this is the alternating harmonic series which converges by the alternating series test. It's our textbook example of a series that converges conditionally. Which I guess you guys had practice figuring out on the homework. Was that the most recent homework asking about conditional? When was that due? Tuesday? So it had a lot of multiple choice questions where there were 3 multiple choices, so you had 2 guesses. So I found people were doing it in pairs, so each person could do 1 guess. If they got it wrong, the other person could do a guess, and if they got it wrong, then they knew that it had to be the 3rd choice. Oh, that was kind of clever, though. I was kind of impressed with. Okay, so this one converges at 10. At the other endpoint, the series is, okay, negative 1 to the n. Now if I plug in 4 minus 7, I get a negative 3 here. Negative 3 to the n over 3 to the n times n. And the negatives, let's see, the negatives cancel each other out, and the 3's cancel each other out. All right, so this all cancels with this. And it's just 1 over n. Also a known series of R's. How many people say this one converges? Okay, I better see a bunch of hands now. How many say it diverges? Okay, good. Yeah, so this one is our, this one diverges. It's the harmonic series. Okay, so putting that all together, right, like if the series was centered at 7, at 10 we decided it converged, at 4 it diverged, so right, that's our interval of convergence, 4, 10. All right. So I'll do another example. I'll do a few examples today on this stuff. We're basically just going to finish up section 10.6 today, and then we're going to spend 2 days on 10.7, which is like the culmination of of this whole class. It's like what the whole class has been building up for. But just so you guys can kind of see every different possibility, let's do another example. How about x to the n over n factorial? Same question. Where does it converge? And I'm presenting this to you now for a good reason, because this exact same series is going to come up again next week. In fact, does anyone know what this equals? Maybe someone who's taken this class for the second time? So you guys are going to find out that this actually equals e to the x. So we'll prove that next week. But for now, let's just find out where it converges. Well, maybe we can make a guess first based on what I've told you guys about factorials, which is they blow up super fast. So the terms of this series have a denominator that blows up really fast. So what would that lead us to suspect? The denominator blows up, so it's like even if we plug in 1,000,000,000,000 for x and raise it to a very high power, 1,000,000,000 to the n versus 1,000,000,000 factorial, which wins? What's here? Okay, 1,000,000,000. What's that? That's 10 to the 12th. What's 10 to the 12th? Let's say, I don't know, how about to the 100th power versus 100 factorial? You know, I don't think my calculator could do this. Oh, did we figure this number out? It was like 10 to the 57 or something. Anyone remember? Or was it 10 to the 1? Okay, well, the top is going to have, you know, I don't know off the top of my head. Maybe I need to pick bigger numbers, but the point is factorials are going to dominate any power of x. And for large enough n, I could definitely dominate the numerator with the denominator. That should be your intuition here, is factorials are going to beat powers of any number, no matter how big x is. So let's just do the ratio test. As usual, that's the usual test we do for terms with factorials in them. Yeah?
What if n is very small and x is very big? Like if x is 2 and n is 1?
Yeah, so That's true. It could potentially be a very big number if x is very big. But all that we care about is what happens eventually. So this sum can equal 1,000,000 to the trillionth power. That's still a finite number. What we don't want it to happen is for it to equal infinity. So you actually don't even care what any finite number of terms of this sum do. You could toss out the first trillion terms of this sum, and the answer will still be the same as to whether it converges or diverges. We only care about what happens at the so-called tail of the sum, and no matter how far you get out on that tail, if it's an infinite tail, there will still be an infinite amount left. It's one of the cool things about infinities. So if I try the ratio test on this guy, if this is like my an, so an plus 1 over an, it'll be x to the n plus 1 over n plus 1 factorial, or x to the n over n factorial. Let's put this in absolute values. That will equal, okay, cancel out all but one of the x's. We cancel out all but one of the n's. And I'm left with x over n plus 1. And the cool thing is that no matter what x is, so even if x was 1,000,000 to the billion to the trillionth power, what's the limit of this quantity as n goes to infinity? 0. So this goes to 0 no matter what x is as n goes to infinity. Hence, what is our radius of convergence? Infinity. This series converges no matter what x is. It converges everywhere. It's a beautiful series. It's so great that e to the x has such a well-behaved series. It's why e to the x is one of our favorite functions in math, that it's equal to its own derivative. It's useful for solving a lot of differential equations, as you guys will see. Those of you that go on to 20C and D and so forth. E to the x has all of these great properties. And this is one of them, that it has a really nice series expansion. Okay. Let's see, what example should I do now? Okay, so let's do some more stuff with the geometric series, which I told you guys is super important in the subject of series and just comes up again and again and again. So let me just remind you of this formula, which I've probably written like 10 times already. X to the n is the geometric series, and it's equal to 1 over 1 minus x. If x is smaller than 1 in absolute value. Okay, so let's sort of like start messing around with this formula and see some of the cool things we can do with it. I kind of did some examples with this last time, but let's try some more. So, thus, how about 1 over 1 plus x? Now pay attention to this trick that I'm about to do. You're going to have to use it a few times. I can write this as 1 over 1 minus negative x. So according to this formula, if I replace x with negative x, this should be the sum from n equals 0 to infinity of negative x to the n. If, and I'm just taking this thing and replacing x with negative x to get this result, okay? If absolute value of negative x is less than 1. But that's the same as absolute value of x less than 1. Oh, okay. So, i.e., 1 over 1 plus x is equal to 1 minus x plus x squared minus x cubed, and so forth, when x is less than 1. Well, that's kind of neat. But why stop there? How about, let's see what else we can do this to. How about 1 over 1 minus 2x? So what should I do to get an expression for this one? How about Yasmin?
Same thing.
Same thing, except now I'll use 2x. And last time I used negative x. Now I'll replace x by 2x in this formula. And I'll get the sum, n equals 0 to infinity, of 2x to the n, which is the same as 2 to the n, x to the n. And this is if this condition, if I replace x by 2x, becomes absolute value of 2x is less than 1, i.e. x is less than a half. So, yeah, in this example, the radius of convergence just got shrunk a little bit, which kind of makes sense if you look at the series. Okay, so we can make this like really sort of annoyingly complicated, so I'll just do one more example of this kind of fast. So how about, okay, 3 over 4 plus 5x squared. Think I could do that same trick with this one? Well, let's see. Let me pull the 3 out. And let's see, I want a 1 right here. So I'm going to pull pull this 4 out. And it becomes 1 plus 5/4 x squared. Yeah? Okay. So this is 3/4 times 1 over 1 minus negative 5/4 x squared. And now you can see that this is exactly the form that I would need it to be in, except now I replace x by negative 5/4 x squared. And this should be the same as 3/4 times the sum of negative 5/4 x squared to the n. Which you could simplify a little bit if you wanted, but I'll skip that part for now. Any questions? All right. Did you guys know that today is Golden Ratio Day? Anyone hear that? It came up in my news feed. I was like, what? No, it's not. It's 6/1/18. But apparently, other countries put the day and then the month instead of the month and then the day. So if you're, I guess, in Europe, the date is 1/6/18, which is like 1.618, which is the first 4 digits of the golden ratio. it's actually equal to 1 plus root 5 over 2. I gave like some extra credit stuff on this. This is just an aside. You guys don't need to know this, but I think this was in one of those 3 blue 1 brown videos, or maybe some.
That's if you put in quadratic equations.
Sorry?
That's if you put in quadratic equations.
Right. Yeah, it solves something like x squared minus x plus 1 equals 0, I think. Yeah, I think I gave like maybe some extra credit problems on this. But anyway, so today is golden ratio day if you live in France. I don't know, it came up in my newsfeed. I thought I'd tell you guys. So now I'm going to show you something that's something pretty neat that we can do with all this stuff. Like, okay. I wanted to show you guys some sort of problems where maybe like solving a real world problem using this stuff, or come up with some funny example. That's why I was reading the news, which is why I saw that. But then I was like, man, no, this material like stands on its own. It's cool enough by itself. So I'm just going to let the material speak for itself here. But let me pose a question. So let's continue to work with this example. I've been bringing it up time and time again, and I'm still going to keep bringing it up. So using 1 over 1 minus x, which, as I just wrote over there, is equal to the sum of x to the n if x is less than 1. Okay, great. Now, let's say that I needed to take the derivative of this function, but I have some aversion to fractions. You guys hate fractions, or like, who likes fractions, right? So let's say I am like violently opposed to fractions. Like, fractions are against my religion, but I still need to take the derivative. So here's the question, is what can I do if I need to take this derivative, but I refuse to deal with fractions? So I want to calculate d dx of 1 over 1 minus x, which, okay, I'll write it. It's 1 over 1 minus x squared. But I need to actually like calculate some values here, but I refuse to deal with fractions. Is there some other way, some non-fraction representation that would give me the derivatives? So like looking at this formula, the top formula, 1 over 1 minus x is 1 plus x squared plus x cubed plus x to the 4th. Here's the question. Could I just differentiate the expression on the right instead? i.e. is 1 over 1 minus x squared, which is the derivative of 1 over 1 minus x. Does this equal, okay, well, let's start taking derivatives here. This will go away. Here I'll get a 1. Here I'll get a 2x. Here I'll get a 3x squared. Here I'll get a 4x cubed, and so forth. Is that a legal operation? Because if it was, then that would solve all my like fraction aversion problems, right? I could just deal with these nice, infinite polynomials. What do you guys think? I mean, I kind of wouldn't have brought it up if it was totally impossible, right? So the answer is yes, under a condition, but it's actually the exact same condition under which the original formula was valid. So the condition was if x is less than 1 in absolute value. So I'm going to give you guys a theorem right now that says that yes, this is okay as long as we stay where x is less than 1 in absolute value. So here's that theorem. So suppose we have some power series. Let's just say centered at some point C. And we have a radius of convergence, R. Right? So F converges on C minus R, C plus R. Then F is differentiable on that same interval. And you can calculate the derivative by just derivating term by term. So, i.e., f prime of x, well, we can actually take the derivative of this pretty easily just using the power rule. So we'll get n a sub n x minus c to the n minus 1 on c minus r, c plus r. So that's exactly what I just did in this example here. I was able to differentiate term by term. And the theorem, our new theorem, says that we're allowed to do that, and the derivative of the left side is equal to the derivative of the right side. So this is all pretty cool. The next question you might add is, okay, I told you you can take the derivative of a series. How about, now, well, naturally, could you integrate a series too? Like, what about going in the opposite direction? So the answer is yes. And I deliberately left like a blank space to write integrate here as well. No, integrate here. So can be derivated or integrated. F is differentiable on blah, 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 and can be derivated or integrated term by term. So the integral of f of x dx is, well, if we integrate term by term, I'll get an x minus c, add 1 to the power, divide by the new power. And let's just put plus c. And again, the rule is on that same interval. Okay, so let's do an example of this, and let me just make sure I'm not skipping anything. Okay, so I told you guys that this Taylor series stuff that we're building up to is about representing functions by infinite polynomials, and we're really going to do that on next week, but we're starting to do that now, right? We've already started to write functions as series. This is this one function which looks like, what does this function look like? It's, wait, 1 over 1 minus x. Yeah, it looks like, this looks like that. Well, it's not actually valid over here, so I'm not even going to draw the graph over there. But in the region where it's valid, it looks like that. So that's our first example of a function that we can write as a series. Here's another one of this function being written as this series. We can now get a whole bunch more using our new theorem, though. So I was doing those examples before of ways I could play around with the geometric series formula. I erased them off the board already, but let me do one more. So here's the problem, or the example, is find a series representation for tan inverse of x. And at first glance, we should have no idea how to do this yet. But if we think about it, we might not really know exactly what tan inverse does or looks like, but we know something about its derivative. That was one of the important derivatives we learned back in the trig substitution section. Anyone remember what's the derivative of tan inverse? Good. Yeah, all right, yeah, you guys know. So if we can get a series for 1 over 1 plus x squared, all we have to do is integrate it term by term, and we'll have a series for tan inverse. 1 over 1 plus x squared, I can do the same trick that I was doing in those previous examples, where I write this as 1 over 1 minus negative x squared. So this is equal to the sum from n equals 0 to infinity of negative x squared to the n, or negative 1 to the n times x to the 2n. And this is if negative x squared is less than 1, but that's the same as x squared less than 1, but that's the same as x less than 1. Okay, so I said we need to integrate this term by term. Right? Like here, I'm just going to write it without the series for a second. Or I'm going to write out some terms of the series for a second. It's 1 minus x squared plus x to the fourth minus x to the sixth plus and so forth. Okay, so let's integrate everything. So the integral of this dx will be the, this is funny notation, integral of infinite series dx, which integrating term by term gives us x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7, and so forth. And on the left-hand side, as we said, that is tan inverse. Am I missing anything?
Plus C.
Yeah, the plus c. And I could write it on the left side or the right side. It doesn't really matter. Here, I'll just write it over here. Although we can actually figure out what c is by plugging in a point. Because I can see that like at 0, the entire right-hand side is going to be 0. You guys know what tan inverse of 0 is? Also 0. Plugging in x equals 0, we see that c is equal to 0. Okay, so I can just get rid of this guy. And actually, yeah, we're pretty much done. That's the whole example, okay? So tan inverse of x is the sum of what? I guess x to the 2n plus 1, negative 1 to the n over 2n plus 1 from n equals 0 to infinity. All right, so we set out what we were tasked to do, which was find a formula for tan inverse. And wow, I can't believe I finished all my stuff like this early.